Hi, I'm a graduate student at Caltech, and I've been interning at Lawrence Livermore National Lab for a bit over a year now. At Lawrence Livermore, I've been working on a piece of software called QBall, which allows us to simulate materials. I'd like to share with you how Julia has been useful in my research, but first I'd like to talk a bit about material science, using software in materials research, and what QBall does. So I get asked pretty frequently what material science is. In materials science, we're trying to understand materials' properties and materials' behavior. When we understand why a material responds a certain way, we can use that understanding to design or engineer better materials. And one of the goals here is that once we have those better materials, whether that means materials that are stronger, more absorptive, more conductive, or what have you, we can use them to build improved technologies. To get desirable materials for a particular application, we might like to search through candidate materials in a variety of regimes. And I'd like to make 2 points about that search. The first point is that we have a huge parameter space to draw from. Now, in defining our parameter space, we have to pick both our building blocks and how we might like to configure those building blocks. In materials research, our building blocks are atoms. So to define material, we need to define its chemical composition, which we can do by taking atoms from different elements in different amounts from the periodic table. And then we can arrange those atoms into different configurations on some sort of spatial lattice. The way in which we arrange or configure those atoms defines our material's structure. Now, between our choices of chemical composition and material structure, or building blocks and configurations, we arrive at this huge parameter space of possible materials to investigate. And at the end of the day, we simply can't build or synthesize every candidate material. The second point is that even if our parameter space were not huge, we still wouldn't be able to run every experiment of interest. We might like to study material conditions like extreme pressures or extreme temperatures that might be out of reach experimentally. So we find ourselves wanting to investigate vast parameter spaces and inaccessible conditions. And while these might be intractable problems in a lab, they're not necessarily intractable on a cluster. So both of these issues motivate sidestepping experiments where we can, and instead using scientific software to run relatively cheap simulations. And at the very least, we can use software to take a first pass at screening candidate materials for a given application. So in particular, the software that my colleagues and I develop and use for material simulation is called QBall, which is an implementation of time-dependent density functional theory, or TDDFT. And I'll get into a bit about what that means and what it does on the next slide. So TDDFT allows us to study dynamic phenomena in materials that occur on very short timescales. When I say very short timescales, I mean timescales on the order of a femtosecond. And for reference, there are 10 to the 15 femtoseconds in 1 second. So to give you a sense of scale for how large 10 to the 15 is, and correspondingly how small a femtosecond is, let's say that you walk about 4 miles per hour and you want to walk 10 to the 15 miles. So to do that, it would take you about twice as long as we've had since the Big Bang. So femtoseconds are pretty tiny, and being able to study material effects on such timescales means that we can study things like radiation damage or the response of a material to light. So we do this by simulating how the electrons in a material evolve with time. So for example, in the video that I'm about to show, we see a crystal lattice populated with gold atoms, as represented by the yellow circles. And a very fast hydrogen atom is going to pass through this target material and excite the electrons of the material, which we'll see is sort of the advent of these blue and red blobs, which means that the electrons are moving around. So to study these sorts of systems, we're using quantum mechanics. TDDFT relies on an approximation to the time-dependent Schrödinger equation. And if you're not familiar, that's perfectly fine. The point is merely that we have some governing equation that describes nature and tells us how the state of our system evolves with time. So in TDDFT, we start with some state of the system, or some state of our electrons at time 0. And we're interested in knowing what the state of the system will look like at some advanced time t. So to get from time 0 to time t, we take a series of smaller time steps, where each time step corresponds to some subproblem. Now, the way in which we would like to improve QBall is that we'd like to be able to march forward in time for reduced computational cost. The point is not only to achieve cost savings, but fundamentally to be able to do science that's currently inaccessible to us, because we can't afford to run simulations long enough to model certain phenomena. So we need methods that allow us to either lengthen our time step reduce the cost of our time step, or both. Now, to do that, we have to screen new propagation methods. And there are many different methods for us to try, but screening new methods directly in QBAL is pretty time-consuming. So QBAL is designed to run on supercomputers with millions of processors, and it's really great at what it does. Now, in the plot that I show here, the number of petaflops per second performed by QBAL is plotted against the number of cores on a blue gene queue. And we can see here that for relatively large simulations of a few thousand atoms, QBAL scales reasonably well up to about 1.6 million processors. Now, the trouble with working directly in QBAL is that to get QBAL to perform as well as it does, it's become a fairly complicated piece of software. So QBAL involves several hundred thousands of lines of code, primarily in C++, and lots of globally shared mutable state. So we want to prototype new methods in a more productive language as a first pass at determining how successful they might be. Now, when I want to implement something quickly, my default language choice has typically been Python. Python is great for a lot of things, but in the past I've hit performance bottlenecks with it when I'm writing anything custom. Rigorously exploring the methods that we're interested in is pretty computationally intensive, and this makes working in Python an unattractive prospect. So I wanted to work in a language that would be time efficient for me both when writing and running code. In other words, the computations that we want to do are sufficiently intensive that we have the two-language problem, not merely between prototyping and deployment, but for prototyping alone. And so I decided to give working in Julia a go. And I was totally new to Julia at the time and needed to take the time to learn the language. But in spite of that, this was still a great choice for my productivity. I basically wrote a toy code in Julia that mirrored the relevant functionality from QBAL and would allow us to play around with different methods. So using this code, we've been able to rapidly screen methods and have made substantial headway as a result. First, we were able to see that there's still quite a bit of room to improve our existing method. Second, we've identified some implicit methods that look promising as alternatives to our existing method. And third, we've been able to rule out some higher order methods that turned out to be unstable for our particular problem. So the story here is that Julia is super helpful in our work on QBAL. We wanted to identify methods that would allow us to more efficiently march forward in time, because this will allow us to do new types of material simulations. QBAL's complexity makes it a suboptimal place to explore new methods, and simultaneously our calculations are too intense for traditional scripting languages. So working in Julia for screening, on the other hand, has helped us to explore much more efficiently and to identify a few promising ways forward. And now, having had the help of Julia, we're able to go back to the QBAL source code and make improvements on a much shorter time scale. So with that, I'd like to thank my collaborators, and that's all. So thank you for listening.